We will come back a little bit later to look at the left-hand rule. Let's step back and talk about reference angles and how we measure angles in general, and then we'll come back to that left-hand rule and I'll try to apply some of that. Here we have coterminal angles and a few other things. So we're going to start off just talking about how we measure angles. Number one, we measure angles when we go around in a counterclockwise fashion like this, like we're normally used to doing. These are positive angles, right? This is the first, second, third, and fourth quadrants. When you go around in order of the quadrants, you get a positive number. If I were to turn and go backwards this way, then the same kind of thing happens, but I get into negative angles. So if I went up, let's just say this is 60 degrees. This would be 60. This would be negative 60. If I went all the way up to here, that would be a positive 90 degree. If I went down, that would be negative 90s. Right? We always measure what we call standard position. We start off with the positive x-axis and go around clockwise, or counterclockwise, or clockwise. That's how we're going to measure all of our angles from or inside the unit circle. Coterminal angles, and the word the prefix co indicates a sharing, right? And so if we were to mark out, let's say this angle here, let's suppose that this angle, we'll keep it in degrees to make it nice. Let's say this is just a 75-degree angle. Okay. I want another angle that can turn that same rotation or end up in the same place. So let's just keep going, right? So if we went around and went all the way back, well, we just went a full circle, right? Plus the 75 degrees. So that would be 360 plus my 75. That would tell me that we were at 400 and that would tell us that we are at 435 degrees. I could also go backwards. I could subtract 360 and get it that way, right? Let's take another angle. For example, let's use one of the quadrants since it's already kind of written there. What if we had an angle where we went all the way up to 90 degrees? What's another angle? We could just go backwards like this. What if we went around this way? What angle would that be? Remember, when you go down, when we go a clockwise fashion around the quadrants, we're getting negative angles. I went through 3 quadrants, right? So that would be equivalent to a negative 270 degrees. Now mathematically, I could have just said, right, and calculate that. That would have been negative 270. So one of the easiest ways that you can find coterminal angles is to take any angle that you're given and add and subtract 360, and that's going to get me 2 coterminal angles. Now, there are an unlimited number of coterminal angles, so I can continue to add 360 every single time, or I could subtract 360, and I could find any number of coterminal angles that I wanted. That's coterminal angles. How do you find the trig functions when we're given a point? So here you have a coordinate, a negative 3, 4 coordinate. So just to kind of remind ourselves, right? And so 3, 1, 2, 3, 4. We have on the coordinate plane a specific angle laid out based on a coordinate, not necessarily an angle measure, right? So I don't know the angle, but we know that if we drop a right triangle, just like we did, and you always want to make this go to the x-axis. So if I'm down below, if I have something in the third or the fourth quadrants, we'll make sure to draw those lines vertically up to the x-axis. Always draw it vertically. We know that this is a negative 3 and this is a 4. Now I know that I'm talking about triangles and I'm talking about physical distance. However, trig functions work all the way around the unit circle, and in order for me to keep their signs correct, I've got to make sure to put the right signs on the x and the y parts of these triangles. And so we can use Pythagorean theorem. Negative 3 squared plus 4 squared is equal to 25. So that means that the hypotenuse is equal to 5. Now, if you recognize your 3, 4, 5 right triangle, you already knew that. But the great thing is, Let's suppose the question had asked me to give me the cosine of this some angle. We don't know what the angle would be here. I don't know the angle, but I can tell you the cosine. The cosine of this angle is the same as the cosine of its reference angle. The reference angle that I'm referring to is this little angle we made with our triangle. If we label the sides correctly, we can find out the exact cosine. And we would do the same thing. It's adjacent, -3 over, not 4, -3 over 5 hypotenuse. And so the cosine would be -3/5. If I wanted to find the sine, it works the same way as well. In this case, we would say opposite 4 over 5. Okay, so anytime that you're given a coordinate like this, -3, 4, you can always find the trig functions of that angle measurement that's made with that point, kind of like we did here, by dropping that vertical line, creating your little triangle, and then just simply answering whichever trig function was asked of you. Since we have all three sides, I can answer any one of them at any time. Okay, I did mention reference angle in that last little part we did. Let's talk about reference angles. Okay, reference angles really exist outside of the first quadrant. In the first quadrant, right, this is your first quadrant, the angle itself is the reference angle. So I'm not really going to talk about the first quadrant here, but reference angles have a couple things. They are always positive. Always positive. They are always between 0 and 90 degrees, right? They will never be 0 and never 90, but they can be anything in between. Now, the majority of the time that we're dealing with these reference angles will always be referring to a 30, 60, 90 or 45, 45, 90. So that's why we call it a reference angle, because it is trying to get you to recognize or refer to a common right triangle, a special right triangle. So if I were to draw an angle here, let's suppose that we have an angle that's like this. Let's suppose that this is 120 degrees. Okay, then what would its reference angle be? The simple fact is the reference angle is nothing more than the distance, the angular distance down to the horizontal or up to the horizontal. We know that the angle itself in this problem is 180 degrees, all the way down to the horizontal. So the question is, how far is it from 120 to 80? We would know by simple subtraction that this leaves a 60 degree angle. Okay, so really what we did here is we took the formula 180 minus my theta, my given angle. In this case, that was 120. Let's try it in the third quadrant. If we were to take another angle, let's suppose it's down here. Let's say this is the angle 225 degrees. Now this works just the same with radian measures, except you would be working with fractions there. It's actually a little bit easier, and we'll talk about those later. Let's suppose that I wanted to figure this one out. We still are looking for the angle to the specific horizontal line here. I still want to know this angle. I don't care which direction you're turning, I just want to know the value of it, because it's going to tell me what kind of triangle would I draw, 30, 45, or 60. And this one, we can say, right, we would end up saying 225 minus whatever's at the origin, or at the x-axis. That leaves me with 45 degrees for the new angle here. So 45 would be there, right? And the idea here is that we took the angle that we had, well, so that would be theta minus 180 degrees. That would give me the reference angle here. If I were to go into the fourth and final quadrant, let's draw a smaller one here. So what if I did this? What if this happened to be 345 5 degrees. What would the reference angle here? Now this one's not a very nice one. I can't do a whole lot with this, but just for practicing, I don't want you to think that reference angles are only just 45, 30, or 60. It could be anything. It could be a decimal even. But let's just talk about the reference angle. We want to know, what is this little tiny reference angle right here? Notice I drew every single angle to the horizontal x-axis. I didn't draw vertical lines. I didn't draw horizontal. I just wanted to know the angle here. We know that this is 360, all the way back at 360, right? So we know that the difference between these two would clearly be just 15 degrees. Okay, so the formula we really use here would be 360 minus the angle in question, minus 345. And that would be how you could find your reference angles for each one. Now, let's be really clear. I really don't focus on these formulas. I don't really remember them. I simply know that I want to know the difference for each one of these. So I just simply subtract the horizontal. If it's, I mean, technically if I subtract it wrong and I get a negative angle, you know that the reference angles are always positive. So you can always find it that way. So why did we learn this? What is the application? For example, just to kind of show you, in the first quadrant, let's suppose that we had this triangle. Let's say we had 30 degrees, and you wanted to know, let's say, the sine of 30. We can always label these 30, 60, 90 triangles. 1, square root of 3, and 2. I can always really quickly tell you opposite over hypotenuse is 1/2, and I've got the sine. But the question, it gets a little more complicated when I move that into a different quadrant. What if I used not this, but what if we had the angle 150 degrees? So the process works like this. I'm going to drop that angle to get myself a right triangle. I can't do it the other way because I don't ever move to the y-axis. So the question is, what reference angle did we create? Well, here we have 180 minus 50. 150 gives me that 30-degree angle. This would make that 60 because the other one is 90. I can, of course, always label in my pieces. That's 1. This is going to be square root of 3 and 2. However, here's the tricky part. Things that I have to remember. When I move around the quadrant, the only quadrant that has all x and y coordinates, that's x, that's y, that are positive is the first quadrant here. So as I move around, I have to make sure that these are x and y coordinate points in the quadrants, right? So it's not just distance anymore. This gets negative. Remember, in the second quadrant, you have a negative x, right? So I'm just going to put the sign negative and positive. In the third quadrant, we know they're both negatives. In the fourth quadrant, we know it's positive x and negative y. So, and it's just a matter of, I need to make sure to add these values every time right here. Okay, so if I wanted to get this, the sine of 150, so we'll do the same as we did before. The sine of 150 is equal to the opposite of the hypotenuse. Oh, it's the same as 1/2. Now, I could ask you for the cosine of 150. That's a little different. That's going to be negative square root of 3 over 2. What if I asked you for the cosine of 30? Oh, that's a little bit different. It's the square root of 3 over 2 this time. Because the quadrants use different signs for each of the x and y coordinates, we have to accommodate those kinds of things. So be careful. Your signs will be positive or negative depending on which quadrant you're in. A little bit more on that in just a second. To keep this idea going, you can go around to any quadrant and apply this rule, defining the reference angle to get your trig function. Let's do another one. Let's this time go into the fourth quadrant. So we had this, right? What if I told you this was the angle 300 degrees, right? So instantly, I'm going to draw my triangle down to the horizontal x. If that's 300, there's 60 degrees left to get back to 360. So I can really say that that's a 60, that's 30. And that means that this is the square root of 3. This would be your 1, and of course your 2. Which ones are negative? Well, in the fourth quadrant, the vertical, if you were following this like plotting a coordinate, if this was a coordinate, you would go positive x-axis, down, negative in the x direction. Or sorry, in the y direction. The y is negative. If I had said, what is the tangent of 300 degrees? Then I would go here and I would say, well, tangent, from what I remember, is the opposite over the adjacent. We come in and we can look at the tangent. We can look at the triangle. The opposite side would be this negative square root of 3 over the 1, and we would just write that in. Negative square root of 3 over 1, or simply put, negative root 3. And that's how we would use that. And this applies anywhere. Real quick, let's go over how this works out with positives and negatives. All trig functions are positive here. Sine and its reciprocal, cosecant, are positive here. Okay? Tangent and its reciprocal, cotangent, are positive here. And then, of course, the one left, cosine and its reciprocal, secant, are positive here. So I remember this kind of as an acronym to kind of help me to remember what goes where, is which quadrants are the trig functions positive. All are positive, so A, S, T, C are all students take classes. And so all of them are positive here. Sine is positive. If they're not positive, then they're all negative. So in other words, sine and cosecant are the only two positive trig functions here. That's one you saw over here. If I found the cosine, that cosine happened to be negative. So I know those. This is kind of a way to give myself a way to check what's going on. So all students take classes, or an easy way to kind of combat that positive versus negative rotation inside the which trig function takes positive or negative values. Okay, this was a lot of information. I highly recommend you go back and watch the pieces that maybe you kind of missed over. And we're going to practice a lot of this stuff, and we're going to see how, if we can get this nailed down in this week before the end of the week. I'll see you guys next time.